Hello everybody. Today I want to talk about fundamental frequency. So in our discussion on signals and systems, we know that a sinusoidal signal can be represented by this. X of t is equal to some arbitrary DC value plus the sum of a bunch of sinusoidal or cosines and these bunches of cosines can have different frequencies, right? But a fundamental frequency is where we have fk, this frequency right here, being reduced such that f sub k is equal to some k times some big F naught. And this F naught is the fundamental frequency. So that means that there is a frequency such that every single cosine in this signal, x of t, share, right? So they share this frequency. And f sub k is called a harmonic of this signal, and k shows that harmonic index. And if we have a fundamental frequency, we also have a fundamental period, which looks like this. Now, a fundamental period is more obvious to see when we graph this in the time domain, okay? And the fundamental frequency is more obvious to see when we graph this in a spectrum representation. Now, how do we actually find fundamental frequency? Well, this is found by taking the greatest common divisor of all of the f sub k's, right? Because we want to see how these f sub k frequencies are related to each other. And so that leads us to our example. So in our example, we're given this addition of cosines, and we want to find the fundamental frequency, and we're going to go ahead and find the fundamental period as well. So you can go ahead and simply just take these radial frequencies and put them into the GCD, into a greatest common divisor, but I'm going to go ahead and turn them into into hertz. So this is 2 hertz right here. This is, this is actually supposed to be 8. And this is 4 hertz right here. And this is 6 hertz. And so our f sub k is equal to this array of different hertz frequencies. And then we just simply take the GCD of this. And it's very obvious in this example. It's just 2 hertz. And so f naught is just equal to 2 hertz. And t naught is equal to 1/2 seconds. So every 0.5 seconds, the pattern repeats itself of this, okay? And so these are the answers. And now, right now, we've just done all the math, and this is pretty abstract. So let me get an image that I created with MATLAB. So this is what the actual signal looks like. Okay, so you can see visually, this is an easier signal, but there are some signals that look maybe a little more difficult to see, but there is a repetition, right? Like, for example, from this point right here to this point right here, we see that it's the same as this point and this point, right? We have the same pattern like this. There's a regular periodic behavior. And so I've marked these two spots specifically, and we can see that the crests, or the highest parts of this sinusoid or signal, are located at 0.47 seconds and 0.97 seconds. And if we wanted to find the period, then we just subtract those two, and we get 0.5 seconds, which is what we found to be our T0. Now, if we were to look at the spectrum representation, which looks like this, we can obviously see, our greatest common divisor is 2, because these are all multiples of 2, and they can all be evenly divided by 2. And I got this. Yep, this is right, actually. Yep. And we can clearly see that this is the first harmonic right here, so k is equal to 1. This is the second harmonic right here, k is equal to 2. And then the third one, k is equal to 3. In this case, we have no k equals 0, because k equals 0 would just be the constant term right here. And that's basically all you need to know about fundamental frequency, because things get a lot more complicated. But if you know that you just need to find the greatest common divisor of all the frequencies of some sum of cosines that produces a certain signal, then you can figure out when is the next time it will repeat this pattern.